Namaste. Welcome to the lecture series on the subject Basic Thermodynamics, Module 5, Part 1, Ideal Gases, Lecture number 9. Myself, Dr. Nsatheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So, we'll continue to solve numerical on gas mixtures. The cylinder contains 0.085 meter cube of this mixture at 1 bar and 10 degrees C. The gas undergoes a polytropic process according to the law PV to the power 1.2 is equal to constant to a final volume which is 1/5 of the initial volume. Determine magnitude and direction of work transfer, magnitude direction of heat transfer and change in entropy. So a cylinder contains 0.08 meter cube of a mixture, at 1 bar and 10 degrees Celsius. So some mixture is there at 0.085 meter cube, which is at pressure of 1 bar and 10 degrees Celsius, and so it is undergoing a polytropic process according to this law PV to the power 1.2 is equal to constant till the final volume becomes 1/5 of the initial volume. That is very important statement. You have to find out determine the magnitude and direction of the work transfer, magnitude and direction of heat transfer, and the change in entropy. So for the given process, P1 V1 to the power 1.2 is equal to P2 V2 to the power 1.2. So from this you can find out P2, because here final volume V2 is 1/5 of the initial volume. So V1 by V2 you will get it as 5, and P1 is given as 1 bar. So if you substitute, you will get P2 as 6.9 bar. Okay. And you have the expression for the polytropic work. W12 is equal to P1 V1 minus P2 V2 by N minus 1, and if you make proper substitution, so you will get the work as minus 16150 joules, or 16.150 kilojoules. So your negative sign indicating that work is done by the surroundings on the gas mixture. That means the work is done on the gas. Okay. Temperature of the mixture at the end of the process, if you want to find out T2, so you have to use the state equation P2 V2 is equal to MR T2. From that you have to write the expression for T2, and if you substitute, you will get the temperature as 390.6 Kelvin. There is another way to find out, or another method rather, to find out the temperature, final temperature of the gas, that is T2 by T1 is equal to P2 by P1 to the power N minus 1 by N. This is a pressure temperature relationship for the polytropic process. So if you rearrange the equation for T2 and substitute, you will get it as same answer, 390.5 Kelvin. Now change in internal energy, that is dU, which is nothing but U2 minus U1 is equal to mCV delta T, that is mCV into T2 minus T1. So mCV and T2 and T1, if you substitute, you will get it as 8.747 kilojoules. Since mass is given, this is the unit is kilojoules. Now by first law of thermodynamics, Q12 is equal to W12 plus dU, or U2 minus U1. So if you substitute, you will get the answer as minus 7.403 kilojoules. So your negative sign indicates that heat transfer takes place from the mixture to the surroundings, because negative means the heat is rejected. So it is 7.403 kilojoules of heat is rejected to the surroundings. So change in entropy of the mixture. So you have the expression S2 minus S1 is equal to M into CV into Ln of T2 by T1 plus R Ln into V2 by Ln of V2 by P1. So here M is known, CV is known, T2 by T1 and R V2 by V1 is known. So M is 0.071, CV is 1.145, T2 by T1, so 390 by 283, and R is 0.423 and V2 by V1 is 155. So if you substitute, you will get the entropy, change in entropy value as minus 0.02214 kilojoules per Kelvin. So it is kilojoules per Kelvin because mass is given, it is not kilojoules per Kelvin. Now let us solve this problem. calculate the constant volume and constant pressure of pressure specific heats of a gas mixture consisting of 1 kg of oxygen, 2 kg of nitrogen at a pressure of 1.5 bar and temperature 20 degrees C. Also determine the change in internal energy, enthalpy and entropy of the mixture when it is heated under a constant volume to a temperature of 100 degrees Celsius. So again a different kind of problem wherein you have to find out the change in internal energy, enthalpy and entropy of the mixture. Now to begin the solution, this is from table C6. He has taken the molecular weight of oxygen and nitrogen. In fact, it is not required because all of you know the molecular weight of oxygen as 32 and nitrogen as 28, but you have to use the table C11 to find out the value of specific heat at constant pressure for nitrogen, which is 1.038, and specific heat of oxygen at constant pressure is 0.917. Now from this you can find out the specific heat at a constant volume by using the expression Cv is equal to Cp minus R. So you have to write for N2 as CvN2 is equal to CpN2 minus Rn2, whereas Cvo2 is equal to Cpo2 minus Ro2. Here Rn2 and Ro2 you may not be knowing, so that but you can find out using R bar by M expression. So this is R bar by M for nitrogen, this is R bar by M for oxygen. If you substitute and simplify, you will get the specific heat at constant volume for nitrogen is 0.741 and specific heat at constant volume for oxygen is 0.653 kilojoules per kg per Kelvin. Now all of you know the specific heat of the mixture is nothing but the summation of the product of mass fraction into specific heat at constant volume for the individual gases. So here only two gases are there, oxygen and nitrogen. So mass fraction of nitrogen is 1/3 and its Cv is 0.653, sorry, this is for oxygen, right, and this is for nitrogen is 3/2 and its specific heat at a constant volume is 0.741. After simplification you will get it as 0.712 kilojoules per kg per Kelvin. Now similarly specific heat at constant pressure for the mixture is also given by the summation of the product of mass fraction into the specific heat of the individual constant gases. So you will get it as 1/3, that is for oxygen, into specific heat of oxygen is 0.917. Similarly for nitrogen 2/3 into 1.038. Okay, so these two values are taken from the table, in fact from C11. So after substitution you will get it as 0.998 kilojoules per kg per Kelvin. Okay, now let us find out the change in internal energy. So as all of you know, delta U is equal to mCv dt. So mmCvm into T2 minus T1 for the mixture. So if you substitute, so you'll get it as 170.88 kilojoules. So this is a change in internal energy for the mixture. Okay. Similarly, change in enthalpy, delta H is equal to mCp into delta T or dt. So mmCpm into T2 minus T1. After proper substitution, so you'll get the change in enthalpy as 239.52 kilojoules. So change in entropy of the mixture, delta S mixture is equal to mass of the mixture into Cv for the mixture into ln T2 by T1 plus R for the mixture into ln V2 by V1. Since the volume is constant, so therefore the second term gets because V2 by V1 becomes 1, so ln of 1 is 0, so this term gets cancelled. So you'll get mm into Cvm into ln T2 by T1. After proper substitution, okay, so we'll get it as 0.5156 kilojoules per Kelvin. Okay, now so we'll solve this problem. A gaseous mixture consisting of 1 kg of helium and 2.5 kg of nitrogen is compressed isentropically in a closed system from a pressure of 1 bar and 27 degrees Celsius to 7 bar. Assuming specific heats of helium and nitrogen to be constant, determine the specific heats of the mixture and the change in entropy of the individual gases and change in internal energy of the mixture. Also find the work required for the compression process. So here you are given the value of Cv for helium, Cv for nitrogen, Cp for helium and Cp for nitrogen. Okay, excellent. So let us solve this problem. So CV for the mixture, so usual formula, summation of MFI into CVI. So it is 1 by 1 by 3.5 into 3.140 for one of the substance, and for other substance is 2.5 by 3.5 into 0.741. just check based on the mass. Okay, mass of the gas divided by total mass of the mixture. Okay, each of these terms. So one gas is 1 kg and other one is 2.5 kg. Since I can't go back to the previous slide, you check out which one is for which ratio is for which gas, and you will get the answer as 1.426 kilojoules per kg per Kelvin. Similarly, specific heat of the mixture, summation of MFI into CPI, I is a constant gas here, so 1 by 3.5 into 5.233 plus 2.53 by 3.5 into 1.038. So this is 2.236 kilojoules per kg per Kelvin. Now gamma for the mixture is nothing but Cp for the mixture divided by Cv for the mixture, so we will get it as 1.568. Now the final temperature of the mixture T2 is equal to T1 into P2 by P1 to the power gamma m minus 1 by gamma m, because this is for the mixture, the ratio of specific heats. So after substitution you will get the temperature as 607 Kelvin. Okay, and the change in entropy of the helium we have to calculate it for individual gases. So delta SH is equal to mass of helium into Cp helium into Ln T2 by T1 minus R helium into Ln pressure of helium at state 1, that is PHE2 by PHE1, and here PHE2 by PHE1 is nothing but the ratio Pn2 by Pn2 1, which is nothing but P2 by P1, which is nothing but 7 by 1. Now making proper substitution, you will get the delta S for helium as minus 0.38 kilojoules per Kelvin. Similarly, delta S for nitrogen you will get it as 2.5 into 1.038 Ln 607 by 300 minus 0.297 into Ln 7 by 1, and after simplification you will get as plus 0.38 kilojoules per Kelvin. And internal energy of the mixture, so delta U for the mixture is mass of mixture into specific heat at constant volume for the mixture into change in temperature, and after proper substitution you will get the change in internal energy for the mixture is 1532.24 kilojoules. Now for a closed system, as all of you know, delta Q minus delta W is equal to du. Since the process is adiabatic, delta Q is equal to 0, so you will get du delta W is equal to minus du. So therefore the work required for the compression process W122 is nothing but minus of du for the mixture, which is minus 1532.24 kilojoules. So negative work indicating that work is done on the system during the compression process, because compression process is always the work is done on the system. Okay, with this I conclude the lecture number 9 on this module 5, and will continue with the one more lecture, that is lecture number 10, and try to solve few more problems. Thank you.